In this problem, I'm going to demonstrate creating what's called a probability distribution. First, I'll imagine 4 people in a room: Alice, Bruce, Claudia, and Drew. And let's give them some outfits. Alice is wearing green, Bruce is wearing blue, Claudia is wearing white, and Drew is wearing red. And I want to define event G as a randomly selected person in the classroom wearing green. So let's tally up those that are wearing green on this day. So we're going to use empirical data here. There was one person wearing green, just Alice. There were 3 people wearing other colors. So let's put their frequencies in. 1 for green, 3 for other colors. Notice that the total number of people being looked at here is 4, and that is n. Now in the past, we had created a frequency distribution where we calculated relative frequencies using the formula f over n. And this is the same kind of idea here. We're going to divide the frequency of wearing green by the total number of people. So the chance that someone's wearing green here empirically is 25%. The chance that someone's not wearing green would be 3 out of 4, or 75%. Now, if we add the probabilities, sum of p here, we get a special number, 1. That means that everybody was taken into account in our table. Okay, so the frequency of the event was 1. That's the number of successes. The number of failures was 3, and the total number of people is 4. Can you know for sure that the empirical probability we found will correctly predict the proportion of people wearing green at the next class? And so the answer to this, I hope is clear, is that it wouldn't be certain that next time we'll find a 25% chance of people wearing green. And just to give an example of that, right now, as I'm recording this video, it's March 13th. And coming up shortly is actually holiday St. Patrick's Day, where people could be more likely to be wearing green on that day than any other day. So that should make it clear that the answer to this is no. We can't be certain that the past results will perfectly match with future results. All right, that brings us to, what is a complement of an event? So complement of event is often thought of as the opposite, and it's defined technically as the set of all outcomes in a sample space that are not included as part of the event E. That would be the complement of E, its definition. So if the event E was it's raining, could you describe the complement of E, which is written as E prime? In words, we might say is not raining. Now, what if we were to do a Venn diagram for E and its complement? What we would have is 2 distinct bubbles, where event E would be one of the bubbles, and then not E would be another. The reason that they don't overlap here is because if you take a particular time of day, it's either going to fall into the E category or not E, and there's no other possibilities. So for that reason, we have this formula. that the probability of event E occurring plus the probability of the event E not occurring adds up to 1. We could also rearrange that formula to solve for an unknown quantity when necessary. Now, some other letters that may be used for this besides E would be P and Q. P typically stands for a probability of success, whereas Q will stand for the probability of failure. So can I use that in question 2 here? It says a weatherman predicts P equals 75% chance of rain. So P is defined as rain. It asks, can you find Q? So first of all, what is Q in words? Well, it's the complement of P, not rain. Okay, so we have the formula that P plus Q equals 1. But since we're actually trying to solve for the variable Q here, that probability, let's rearrange the formula to Q equals 1 minus P. Now we could keep the P in percent form or change it to decimal form. I'm going to change it into decimal form, and 75% is the same as 0.75. So if we just subtract them two, we get 0.25, which is a 25% chance of it being dry.